Hi everyone, welcome to Sprint 3, AS Maths. We're doing a Pure 1 paper today. Okay, so we're going to start out with some basic Trig. So all they're asking is that you understand how to apply the identities that are in your formula booklet. So you just have to use those exact ones. So they've given you some letter to represent the sine of theta, and you have to now re-express basically all of these things in terms of sine of theta. So, for example, for this one, you need to use the identity that sine squared theta plus cosine squared theta is equal to 1. And if you solve for cosine theta, you get that cosine theta is equal to the square root of 1 minus sine squared theta, which is square root of 1 minus k squared. So just stuff like this. Tan theta is the same. What does tan theta equal? Well, it equals to sine theta over cosine theta. And you already know what sine theta and cosine theta are in terms of k. You know, they've given you one, and here's the other. So that's very easy for you. This one, it's just a double angle formula. So if you go to the formula booklet, and you'll see the one that looks like sine of a plus b is equal to sine A cosine b plus cosine A sine b. And then you notice that, here A is theta, B is pi. So what is the cosine of pi? Well, it's minus 1. What is the sine of pi? Well, it's 0. So that term disappears. So you've got minus sine of theta, which is minus k. And that's all they require from you. So it's just pumping through the formula booklet stations. Okay, so here we're given a curve and some lines. And we're asked, first of all, to find the area of this triangle. So you just have to think about this geometrically. And for this one, I mean, it's only a 2-mark question. It's not that bad. But you can see that this base, well, how long is this base? This section is P, and this, I mean, x is minus 2. That means that this must be 2 units long. So the whole thing is 2 plus P. And then the height, that's what we have to find. And we know that the point Q is on this line, y equals 2x squared. That means that the x and y coordinates of Q, qx, qy, must obey this equation. So what is the x coordinate of Q? Well, we know it's directly above P, so it must have the same x coordinate. So therefore, qy, which is equal to 2qx squared, is equal to 2p squared. So this is 2p squared high. Well, then that's all you need to do. You know that the area is going to be 1/2 height times base. The 2p cancels with that. So that's fine. Now they're asking you to do something a little more subtle. And they're asking you about rates of change. So this is almost always going to indicate that you need to use differential calculus. So the point P moves along the x-axis at a constant rate of 0.02 units per second. So what they're saying is that this point here is going in that direction. And so is this one. This one is moving up the curve in such a way that it's always going to be directly above P. So therefore, the area of this triangle is obviously going to change, right? Because now it's this big guy. So they're asking you to find how the area changes. Now, when P changes, when this point P changes, what is causing it to change? Well, it's still moving on the x-axis, so only its x-coordinate is changing. So you've got this little p, which represents the x-coordinate of big P. That's the thing that's changing. So how is it changing? Well, it's changing if we say sort of dpx dt. Well, px is just little p, so dp dt, and that's equal to 0.02. So that's what we're given. Now we want to know how the area is changing. Well, the area just depends on p. Like it doesn't depend on anything else. So all we have to do is differentiate this. So we start out with area is p squared p plus 2. And we're going to differentiate this with respect to time. So we have dA dt is going to be equal to, okay, and you may have a favorite way, but sometimes with these polynomials, it's better just to multiply everything out, and you'll see very clearly what the derivative is. So this is the chain rule. So let's define this as f of p, and then if we want df of p dt, well, that's df of p dp dp dt. So this is the chain rule, right? So I differentiated a with respect to p and then multiplied that by the derivative of p with respect to t to get the full derivative. Well, we know what dp dt is. It's 0.02, and they told us what p is. And that's all you need to get the answer. Okay, so this question is really not worth spending any time explaining, because it's literally just plugging stuff into the formula in the formula booklet. So this is just, binomial expansion. I will maybe just spend a few seconds just reminding you that there are a lot of ways to expand formulas, expressions, and functions. And the binomial expansion is one of these, and it works when you have a positive integer as your exponent. Like if you have something that looks like this, and it's a finite series, so it's a series of terms, and there's not an infinite amount of them. There's a finite number, and they're given by the formula in the booklet. So, for example, this 1 minus x to the power 6 would go something like 1 plus 6 choose 1 times plus 6 choose 2 times x squared plus 6 choose 3, and so on, minus x cubed plus, and there would be a bunch of terms, but there would be a finite number, versus something like the Taylor expansion, which comes on a bit later, which is an infinite series that only sort of gets better and better at getting close to what the function is, but never gets there with a finite number of terms. Whereas a binomial expansion, you will get exactly the right, the expansion, the same way that if you multiplied out a quadratic like this, you would just get 3 terms. So what they're looking for is that you write this out, and then you work out, what these coefficients are. So this is a coefficient. These are all coefficients. When you multiply out this one, the coefficient, there'll be a 2 coming in here, and they will, instead of a minus sign. So it will be exactly the same formula, except inside each of these things would be a 2x instead of a minus x. But in that case, the 2 would become part of the coefficient. So the series is like a0 plus a1x plus a2x squared plus. So every power, this is called a power series, because these are in powers of x, as in like 0th power, 1st power, 2nd power. X squared is 2nd power. So they all look like this, but a Taylor expansion will go on forever. Binomial expansion will have a finite number of terms, and these things are the coefficients. And it can be quite a profound result to examine the relationship between the coefficients. But for now, they're asking you to find the coefficient of x squared. So basically, you just need to find all the matching pairs between your 2 expansions that you've written down, or the first 3 terms. You only need the first 3 terms. And you just match between them the ones that could combine to form an x squared. So maybe a 1 and an x squared. Or so this will be the x term plus something, x cubed. So you'll see that between 1 plus, so this is like series 1, this is series 2. So there'll be, if you times the 1 by the x squared, that'll give you an x squared term. If you times the x by the x term, that'll give you an x squared term, or the x squared by the 1. So those will all give you x squared terms. The x cubed won't enter into this at all because you'll always find that'll always be, you know, x cubed or above, like always be a higher order of x. So you just want the x squared ones. And that's it. Okay, so vector question. So this first one is purely asking you to understand what a dot product is. So a dot product, we call it the dot product because there are two types of products with vectors. Now, we call it a product in the same way that multiplying two numbers together to, you know, scalar multiplication, we call that the product of two numbers. But when you're asking about multiplying a vector by another vector, you have to actually explain what you mean because it's not obvious. It doesn't, in fact, it's not defined until you define it. Like it's not a basic extrapolation of multiplying together two numbers. You have to actually sort of clarify what you mean by taking a product of two vectors. And actually, it's been convenient for mathematicians and physicists to define two types of product. You have the dot product, also called the scalar product because it gives out just a number at the end, versus the cross product, also called the vector product because it gives out a vector at the end. So these are two completely different operations, but they're both called product because they're both kind of multiplication-ish. But you can't multiply two vectors together the way you would multiply two numbers. It doesn't make sense. So in this case, the dot product has two, so it looks like this, v dot w, and you have two ways of defining it. You can talk about it in terms of the components, so like v1 w1 plus v2 w2 plus blah, 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 whatever your dimension of your vectors is. Like here, they're three-dimensional. So it'll be v1 w1 plus v2 w2 plus v3 w3. But it could go on if you had like long vectors. But this is also equal to the magnitude of v times the magnitude of w times the cosine of the angle between them. So you know the components, so you can easily get this expression. And you know how to work out the magnitude. If you need a reminder, it's just, it's just Pythagoras. I shouldn't call it x and y because that's not very general. But v1 squared plus v2 squared plus v3 squared, blah, 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 all square rooted. In the same way that if you want the hypotenuse of a triangle, these are just, kind of coordinates of the sides of some multi-dimensional triangle, and you're looking for the length thing itself is hypotenuse. Just think of the two-dimensional case. If I go across and then up, that's a vector. The length of my vector is that. That is the actual vector. So, so you know how to work out the magnitude. So magnitude of v times magnitude of w times the cosine of theta, and you just solve for the cosine of theta. So, once you've done that a few times, I don't think you'll really forget. So now they've given us a third vector with this unknown k, and they've told us that AB and OC have the same length. Well, first, what is AB? Well, AB, the line from A to B, if we just remind ourselves, imagine that, okay, I'm not going to do it, do it accurately, but let's say here's one point and here's another point. Let's call that A and that B. And I draw a line between them. I want this vector that goes from A to B. Well, to get from A to B, I have to, it's perfectly fine for me first to go to the origin and then to go up to B. Well, going from A to the origin is minus OA because it's the vector go from the origin to A is is OA. If I go backwards along it, that's minus OA. And then from the origin to B, well, it's just normal OB. So the vector from A to B is minus OA plus OB. So in that case, this is minus 3 plus 6. So we will get, I think, 3 minus 3, 6. And what is the magnitude of this? Well, we just use the Pythagoras thing again, and we get some number. And then we're told that OC has the same length. Well, we can use exactly the same operation on OC. We'll say OC, it's going to be equal to k squared plus 4 k squared. And this is all going to be square rooted. Plus, and then this thing squared is, 4k squared minus 12k plus 9, all square rooted. And you know these, whatever that was, and which is going to be a number, and whatever this is, are going to be the same. So you can like square both sides to get rid of the square root, and you'll end up with two possible values of k because it's a quadratic, right? So set them equal and then square both sides. Okay. Okay, so here we've got a piece of wire and it's bent from the perimeter of a sector. Now don't get confused, they didn't mean just the arc, they mean the whole thing. That confused me for a bit, but the whole pizza slice, this is wire all the way along the perimeter. Now the area of a sector of a circle is given in the formula booklet, I believe. So the area is equal to 1/2 r squared theta. So let's call this is theta. And we also know that the perimeter of a sector is just equal to r theta plus so this is the arc length is r theta, and then this one is r and this one is r, so it's 2r. And we know what the perimeter is, right? We know that it's equal to 24. So if you just solve for this, plug in, if you solve for theta and then plug it in, you will get that a is equal to, it's equal to that. So you just use these two relations. Yeah, so in the next question, they're asking you to do what is essentially completing the square. So we start out with a is equal to 12r minus r squared. Now we want to pull this into a bracket. So there's a minus in front, so we'll say minus. And then my bracket is going to be r minus. Now, the general formula for this is like, all the procedure is that whatever is in, so you have some quadratic with an r squared, whatever is in front of just the r, like not r squared, just the single r, the thing inside the bracket is going to be half of that, because you're going to get two copies when you multiply out the bracket. So if you see what I mean, r minus 6 all squared, if I square this, I will get a minus r squared, and this will give me minus 2 copies of 6r, which is 12r, and then we minus becomes a plus. But I'll also get a constant term, a non-r term, just a single number term, and that doesn't belong there. Like it's extra, so I have to account for it. So here I will get an extra minus 36, so I have to go plus 36 to account for it. So now we have this. We can solve in this question. We can solve for the angle. Given that r can vary, state the greatest value of a and find the corresponding angle of the sector. So what they mean is, like, you can divvy up the perimeter between the arc and the radii. And they want to know what one will maximize the area. Well, obviously this is going to be a calculus question. So you just have to differentiate dA, dr. So you're varying the radius. That's what's changing. And you want to see how A changes when you do that. So that's just going to be equal to 12 minus 2r. And stationary point, maxima, dA, dr is equal to 0. Now, in fact, maxima or minima, any stationary point will have dA, dr equal to 0. But if you look at this guy, you can sort of see that setting it to 0 will only give you one solution for r, and that's r is equal to 6. So if you do the second derivative, you'll find this is equal to minus 2, which is less than 0. So there's only one stationary point, and it's a maximum. So maybe you want, if that sounds very strange to you, maybe you want to watch some of the previous sprints videos on. I think in the first week we covered. We really went into detail about stationary points, maximum, and what it means for the derivative to be the gradient of a curve, and what it means for it to be increasing and decreasing around a point. But it's worth understanding that in detail. Anyway, so we've got the radius, the max radius. That'll give us the maximum area. And then you can solve for theta using this, or this one, or either one. Okay. So here we're wanting to find some relationships. I mean, I always think of it in terms of vectors, but there's obviously an intimate relationship between vectors and equations. They're just both ways of looking at curves in a space. So they've given us one of these points, and they're asking us to visualize it in a graph. So let's start with an equation. We have this line with a gradient minus 2. So let's look for I think that's a good clue to look for the equation of the line. So it's going to be y is equal to minus 2 x plus c, where c is the constant. Now we know that p is on the curve, on this line. Therefore, it must obey this equation. So we have that 2t is equal to minus 6t plus c. So c is equal to 8t. So that's our line. Y is equal to minus 2x plus 8t. Well, all well and good. So now we can get information about this curve. So let me just draw. Actually, we don't really need to do it. We know that a is the x-intercept and y is the b-intercept of this line. Well, the x-intercept is reached when y is 0, right? So when y is 0, so a has 0 as y-coordinate, and its x-coordinate is when y is 0, so blah, blah, blah. We find the x-coordinate is 4t, comma 0. And b, well, that's the y-intercept. Well, that's reached when x is 0. And when x is 0, y is equal to 8t. So they're asking you for the area of the triangle AOB. So we've got our y-intercept at b, our x-intercept at a. I mean, this is not necessarily accurate. And, oops. And they're asking for this triangle. Well, obviously, the base of the triangle is going to be 4t, and the height is 8t. So the area is 1/2 base times height. No problem. So now they're saying there is another line and it's perpendicular to this AB and intersects the x-axis at C. So it's perpendicular, so it comes in like so, and it intersects over there. I'm not claiming this is accurate in terms of numbers because we don't really know what the numbers are because T could be anything, but just strategically. And this is P, the intersection. So we're told that it's perpendicular. And what do we know about perpendicular lines? Well, if two lines are perpendicular, then the gradient of one times the gradient of the other, the product is -1. So, I mean, so in this case, our y prime, which is our new line, is equal to 1/2 x plus c. And again, we know that the p will sit on this line. So therefore, if we plug p's coordinates in, that'll be valid, and this gives us that c is equal to 1/2 t. So y prime is equal to 1/2 x prime plus 1/2 t. And the x-intercept of this thing, well, it's when y is equal to 0. And you just get that, so c, so it intercepts the x-axis, the y coordinate is 0, and then the x coordinate is -t. So that's just by plugging in y is equal to 0 into this. So this is the c coordinate. So now they're asking us about the midpoint of the line CP or PC. Either one is fine. So let's look at the line CP. Well, as we saw before, the line CP is given by -OC plus OP, which is going to be T0 plus P's coordinates, which are 3t, 2t, and that's equal to 4t, 2t. So that will take you from C to P. Well, what if I don't want to go all the way to P? What if I just want to go halfway up, which is the midpoint of this line? Well, if I want to go from the origin, let's draw that again. So here's C, here's P, here's the line. If I just want to go to this point M, say, what I can do is I can just go to C, and then I can go halfway up the line from C to P, and that'll get me to M. That's the same thing as just going straight in terms of vectors. It's exactly the same thing. So the point M, or the line from O, the origin to M, is given by going to C first and then going halfway up the line from C to P. Well, that's just T0 plus 2t, t. No problem. Which if you, sorry, 2t, oh yeah, sorry, minus t. Right, which gives you the line t, t. Well, if m has the coordinates tt, then it obeys the equation y is equal to x. So it will lie on this line, y is equal to x, because a line which is given by an equation is just what we call the locus, but it's like it's a set, and it's an infinite set of infinitely many points, all of which obey. So any point that obeys that equation is on the line. There's so many of them that they're so close together that they look like a solid line. In fact, they are. So if you show that the coordinates of M obey this equation, it means it's on the line that is defined by that equation. Okay. So this question's about geometric. It's about progressions, about series. So the important thing is always to remember that let's look at the geometric one first. So geometric progression is like defined by the idea that if you take any part of the series, any particular term, and divide it by the previous term, you will always get the same number. So if I take the 5th term and divide by the 4th term, I will get, and I get 5, for example. If I took the 279th term and divided by the 278th term, I would also get 5. So essentially, each time you go along, you are multiplying by a number. And that number could be, if a number is smaller than 1, if it's a fraction, for example, or a decimal, some fraction of 1, then each term is going to get smaller, right? If I take something and I times it by half, the same thing as dividing it by 2, then each term will be half of the previous term, and so the thing will kind of get smaller and smaller and smaller, and that's what we call a convergent series, because it will, it'll tend towards a particular value. And if you sum it to infinity, what that means is sort of saying which value is it getting closer and closer and closer and closer to. If your ratio, your common ratio, the thing you're multiplying by, is bigger than 1, the thing doesn't have a limit. It doesn't have a sum to infinity except for infinity itself, because each term gets bigger and bigger and bigger and bigger and bigger, and you just keep adding more stuff. You just get closer, you approach infinity. But the ones that deal with here are, if there's a sum to infinity, that means that the ratio is less than 1, and that this thing is converging on a particular value, the sum to infinity. So what does that mean? Well, I like to just remind myself that a geometric progression looks like this. It starts off with a first term, some number. And the next term is just that number times the common ratio. And the next term is that previous number times the common ratio, which we've got r squared now, and so on. So you see that to define a geometric series, all you need is 2 things. You need to know the initial value, and you need to know the common ratio. So we have 2 unknowns, and the sum to infinity is a over 1 minus r. That's in your formula booklets. So for this, you need those 2 terms to be able to know what the sum to infinity is. So we have 2 unknowns, and we have 2 kind of equations. What are these equations? Well, they're telling us that the 3rd term, so what's the 3rd term? It's this guy. They're telling us that a naught r is equal to 1/3. And they're telling us the 4th term, which is a naught r squared is 1/3, and a naught r cubed is 2/9. Well, these are 2 equations, and we have 2 unknowns, so we can use this to solve. So I'm going to take this guy and divide it by that guy. And that means that I get the a naughts cancelled, r cubed divided by r squared, it gives me r is 2/9 over 1/3, which is 2/3. Hey, that's a good cross check, because now we expected that the common ratio was going to be less than 1, and it is. It's 2/3. So that's great. That means we're going to get a convergent series. And then we just plug that back into one of these things, and that gives us a naught. There's 3/4. And then you just plug it into that to get the sum to infinity. And that's all there is to that. So the next one isn't about a geometric series, it's about an arithmetic series. And that's when, instead of multiplying by the same thing each time, you are adding the same thing each time. So you can write it out again in general as some initial term plus the initial term plus a. In fact, let me just be a little bit, no, let's not call it a because they're both called a, that's dumb. Let me just be a little bit suggestive and say we start with our initial term theta naught, and then we go, the next term is theta naught plus a, and the next term is theta naught plus 2a, and so on. I'm actually going to write them all out because there's only 5 sectors, so it's not like it goes on forever. It actually makes the question a little clearer if you write them all out, because we're told that there's a finite number. So the area of a sector of a circle is 1/2 r squared theta, as we saw before. And we're told that the angle of the largest sector is 4 times the angle of the smallest sector. Why did I? Okay, I don't know why I gave you the area there. I think that was from a different question. Okay, so we're told that the angle of the largest sector, well, these are each of these is angles. That's the initial angle. This is the second angle. This is the third, fourth, fifth. So this one's the largest, right? And we're told that that angle, theta naught plus 4a, is 4 times the angle of the smallest sector, which is theta naught. Well, if we just solve, we get that that a is equal to 3/4 theta naught, but that's just a step along the way. We still need to solve for the rest. So we had two unknowns, right? We had theta naught and we had a. This was one equation that we were given, so we can't quite solve. Like if you have some number of unknowns, you need exactly the same number of equations to be able to solve for all the unknowns. So we have two unknowns. This was just one equation, so we can only solve for one of the unknowns in terms of the other one. But there's an implicit equation. There's another equation which is available to us. They just haven't stated it. But just think about it. This is a circle, so you can't just have angles being any arbitrary size. We know that this thing has been divided into these 5 sectors. There's no little extra bit left over. There's no making the circle bigger or having somehow the circle having extra angles or anything. A circle always has 360 degrees. So the sum of all of these must be 360 degrees. Well, how many copies of theta are there? There's 1, 2, 3, 4, 5 copies of theta in the sum. So we know this whole thing is equal to 360 degrees. How many a's are there? Well, there's 4, 5, 6, 7, 8, 9, 10. And that gives us, if we then substitute in for our value of a into there, you could easily solve for, this will give you theta naught. So they want you to not forget, so theta naught is going to be 28.8 degrees. But that's the smallest angle, right? You will lose a mark if you forget that they asked for, given that blah, 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 find the angle of the largest sector. So they want you to find this guy. So first you have to, so you started with 28.8. So anyway, we have theta naught plus 4 times whatever alpha was, 3/4 theta naught. The 4's cancel, 4 theta naught. Actually, that's pretty obvious from this part of the question. The largest sector is 4 times the angle of the smallest sector. Anyway, you see how to do it. Okay. So, function. We have a function which includes a trigonometric function, and we're told that it's defined for x between 0 and 2 pi. So we can get that this is so this cosine of 1/2 x. Well, okay, we'll see it in the question in a second. So they want us to solve this equation, giving the answer correct to blah, blah, blah. And I'm going to do it in kind of full exhaustive. I'm going to be very rigorous about it, even though you don't really have to for this exact question, but let's just do it. So part 1, let's do this in detail. If we solve this, so we have f of x, which is equal to 7, is equal to 5 plus 3 cosine of x over 2. So I'm just going to simplify this a little bit and say that the cosine of x over 2 is equal to 2/3. Now I've kept it like this so far because I want to make it clear where these, often in these questions you get more than one solution, and that's because of the periodicity of cosine. So let's see what I mean. I'm just going to, I'm going to define y, or no, I'm going to define, I don't know, p, and I'm going to define that. That's what the 3 lines mean. It means I'm defining this as x over 2. So we have that the cosine of p is equal to 2/3. Well, imagine that this is p. Now, if x is going between 0 and 2 pi, then what is half of x going between? Well, it's going between half of 0, which is 0, and half of 2 pi, which is pi. So we're only looking for a graph up to pi. Now, the cosine function is periodic in 2 pi. So, the cosine function looks like this for 2 pi, and this is pi. So that's what it looks like. It's the first half of the cosine function. And they're saying yes, p is running from, yeah. So they're looking for the value for which the cosine is equal to 2/3. So in this case, this is a one-to-one function. So you don't have to, so even though cosine is periodic, so that it would say 2/3, maybe that point is over here, it would repeat itself once you got over there. But because we're limiting x between 0 and 2 pi, that means we're limiting x over 2 between 0 and pi. The 2/3 only appears once. So it's always best to draw these diagrams and realize that the periodicity comes from the cosine. This thing, it has a more complicated, the whole thing with the 5 times 3 and then plus 5 at the end, that's got a much more complicated behavior. It still repeats and still has a periodicity, but it's a little more difficult to deal with. So I would solve it first in terms of the trigonometric function, and then sometimes, what if this thing had to find itself between 0 and 4 pi? Then the p would be between 0 and 2 pi, and we would have two values, and we would have to mention them both. In this case, we only have one value, the principal value, this one. And if you put into your calculator, this thing into your calculator, you'll get that x over 2, p, which is x over 2, is equal to 0.84 radians. So x is equal to 1.68 radians. And that's the only answer. The next time the 2/3 came up, x would be 10.88 radians, which is out of its range. But this is in the right range. Okay, so then they want us to sketch the graph of this function. So we've kind of pretty much done it already, but let's go through it again. So this is our f of x, this guy. So let's think of the cosine function. Well, we already drew it here. So the cosine of x over 2. So we have to have x on this axis now. If x over 2 is pi, then x must be 2 pi, right? And that's the range that we want anyway. Now, in fact, let me draw this in various stages. So yes, right. So these are going to be our various as we improve our understanding of this function. So initially, we're just graphing cosine of x over 2, and that's just what we graphed before, like so. 2/3, and now we're going to multiply it by 3. Like that's the next thing. So let's now graph 3 cosine x over 2. Well, all that does is stretches. It's kind of going to look the same, but it's actually going to be stretched. So it's going to have a peak at 3, and our 2/3 point is going to now be at 2, and it's going to have a trough at -3. So originally it was a trough at -1 and a peak at 1. Whoops. Okay, so it's just stretched, no problem. Now the final thing is to add 5. Well, that means that whatever I have at any point, I'm always adding 5 to it to get my y value. So if I have an x, if I have 3 cosine x over 2, which is like something here, that gets shoved up by 5. So now our trough was at -3. That gets shoved up by 5. It goes to +2. So there'll be over there. And then our peak was at 3. Well, now it's going to be at 7. And otherwise, it's going to be the same. So I know these things look very different, but you know, it's a sketch. You don't have to be crazy about it, as long as it looks vaguely the right shape. So 7 and 2, and you mark. So this is the full function, f of x. Okay, explain why f has an inverse. Well, all you need to say is that within the range of f, so remember the range was within the domain of f and its range, it's a one-to-one function, right? There is no faffing around with parabolas where, you know, you can go from x to y, but once you're at y, so say this was, you know, y is equal to x squared, this parabola. This is not a one-to-one function because x is equal to 1 and x is equal to -1 give the same value of y. So if I told you that y was 1, you wouldn't be able to tell me whether I was over here or over here. So it's not a one-to-one function, so it doesn't have an inverse. The inverse is telling you how to go back from y to x. Here, you can. For any single value of x, there is only one possible value of y. And for every value of y, there's only one possible value of x, which it could have come from. So therefore, it is a one-to-one function. One-to-one. Therefore, there exists an inverse. And now they're asking you, the very last question, they're asking you how to, they're asking for an expression for that inverse. Well, there's just the way to do this is just to kind of switch x and y, and then solve for y again. So initially we had y is equal to 5 plus 3 cosine x over 2. And now we're going to write, this becomes x is equal to 5 plus 3 cosine y over 2. And you just solve, you know, add things and subtract things and take inverse trigonometric functions. Okay. So we're given an equation of a curve, and now we're asked to find stationary points. So we've seen stationary points a bit in this paper and in previous papers. So the way to do this is, of course, to differentiate, as always. So let's talk about dy dx. Well, that's just 3x squared plus 2px. And we're told that, and we know that for a stationary point, y prime is equal to 0. So this is equal to 0 when evaluated at a stationary point. And then we solve this and we get that, well, we'll just take an x out and we get 3x plus 2p is equal to 0. So you know, don't divide by x unless you're sure that x is not 0. Like, you can't divide by 0. That's one of the big holy laws of mathematics. You literally cannot divide by 0. So don't just, what they say is take x out. So take it out of the bracket. Don't divide by it and throw it away, because it's a valid solution. Like, x equals 0 could be the answer. So what this makes clear is that x is equal to either x is equal to 0 or x is equal to minus 2p over 3. And x is equal to 0 is what they mean, the origin. And we can see that because if we plug the x equal to 0 back into the original equation, we get y is equal to 0. So for this one, y is also equal to 0. Well, that's just the origin. And the y coordinates of this, well, it's going to be 2 minus 2 over 3p cubed plus p times minus 2p over 3 squared. And you can solve for that. So now they want you to find the nature of the stationary points. Well, the nature of the stationary points is just all decided by d squared y dx squared, the second derivative. And this is equal to 6x plus 2p. So if you look at the x is equal to 0 point, that gives that y prime prime is equal to 2p, which is greater than 0, because they've told us that p is a positive constant. So positive means that p is strictly greater than 0. It means it can't be 0. And that's important, right? Because the rules for stationary points, for like evaluating their nature based on the second derivative, if the second derivative is 0, you've got a saddle point. You've got a, some slightly funkier point. So for maxima and minima, maxima it's got to be less than 0, and for minima it's got to be greater than 0. So this thing is greater than 0, so this has got to be a min. And what about the other point at minus 2p over 3? Minus 2p over 3, we get that this thing is, if you plug it in, you'll see that it's equal to minus 2p, which is less than 0, so this is a max. So that's done. Now they're saying they've got this other curve with p in it, and then find the set of values of p for which this curve has no stationary points. Well, it's pretty much just exactly the same as what we've done, right? We're going to say that y prime is equal to 3x squared plus 2px plus p. And we're saying that this is equal to 0 for a stationary point. So we can then solve for x using the formula, right? It's going to be equal to minus something, 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 plus or minus square root blah. This thing inside, this del, the discriminant. You should have seen this before, but if you haven't, now that's the thing that sits inside the square root after the plus or minus signs. So the whole reason that we have various values of x, 2 possible values of x, is because of this plus or minus sign here. One where you take the positive option, one where you take the negative option. Now, if the thing after the plus or minus is 0, then it doesn't make any difference whether you take the positive or negative option. That's when you've got x is equal to 5 or x is equal to 5. They're both the same. And that's when you have like a parabola just touching the x-axis, for example, because it touches it at both these points. Maybe this thing is like some positive number, in which case you're going to get plus or minus. They're going to be 2 different answers. You've got one of these where it cuts the x-axis like so, and you've got 2 solutions. But if it's negative, then you've got a square root of a negative number. And if you're in the real numbers, which we are for AS Maths, this is undefined. It doesn't exist. You cannot have the square root of a negative number. Now, if you're talking about complex numbers, then suddenly you've got some more options available to you. But essentially, so this one over here was del greater than 0. This was del equal to 0. This is del less than 0. Looks like this. So it just doesn't cut the x-axis. And they often write this. I mean, when I was a kid, they would say, oh, that means that there are no real solutions. And this was long before I knew that there was anything other than a real solution. Like, why would you bother saying real? Like, of course, you just say no solutions. And they were like, well, no, they kind of technically are solutions, but they're to do with complex numbers, so don't worry about it. So what they're saying here is that they want a value of p for which the curve has no stationary points, and that means that del is less than 0. And here del is just so it's the bit underneath the square root in the formula. So it's got to be b squared, which is it's 4p squared minus 4 times 3p. And they're saying that is less than 0. So this will give you a range for p. Okay. Last question. So here we're given a curve. So this is an integration question. They're going to ask us to integrate areas and things. Now this is, that'll be the very, very final question. So I'll talk to you about that in a second. So we're given 2 straight lines and a curve. like so. Find the coordinates of B. Well, I'm going to call this curve YC, XC. So we are told that the normal to the curve is this line here. So we know that the gradient of this line has a relationship with the gradient of the curve at that point. You know, it's always at right angles, which means that always means right angles means that the product of their gradients is -1. So what is the gradient of the curve at this point, at this instantaneous point? Well, for this, we use differentiation, of course, and we get that dyc dx c is, as we get -4 times 3 is 3xc plus 4 to the -3/2. That's just differentiation practice. Except in substitutes, you just have to do it a bunch of times. And then we're going to evaluate this at A, because we're looking, this is a general expression for the gradient of this curve, which is valid anywhere on the curve. But now we want to evaluate it at a certain point and know what the gradient is at that exact point. And that's equal to -3/2. So therefore, we've got this. So this is going to be y is equal to 2/3 x plus c. And if you plug in a, you can find out what c is when it turns out to be 4. Well, obviously, it's the y-intercept, it's 4. So now, we know that this is that's the equation of this line, and we know that b is on that line, and we know the x-coordinate of b. So all you have to do is plug in the 4 there, and therefore you'll get that the y-coordinate of b is, you get this 2/3, and we know that x is 4 plus 4. That's equal to 20/3, and that's done. Now the second part, it says show with all necessary working that the areas of the regions marked P and Q are equal. See the pizza slice. So the idea here is that integrating a curve gives you the area under a curve. So what is the area of Q? So the area of Q is the area of the sort of big semi-house minus the area of P, right? So the thing to integrate is the thing to integrate first, the hard thing, is AP. Well, that is just the area under this curve. The curve which has a formula given by this. So we just we have to know how to integrate this. So I'm going to just rewrite it as 8 times 3x plus 4 to the -1/2. Now this is actually not that bad to integrate. Like it's I don't know if you see it yet, but like it actually, these kind of 1 over square root of stuff, like that's actually pretty easy to integrate. So let's take this guy down here. So the area of P is the integral from, I've forgotten the limits, dx, of 8 3x plus 4 to the -1/2. And the trick here is to think about what could have led to this -1/2. Well, you're probably used to seeing that when you start out with something that's to the power of a half, i.e. a square root, and you differentiate it, you end up, it's a half minus 1, which is -1/2. You end up with a square root on the bottom. So that's what's happened here. So let's pull the 8 out first. Who cares? And now imagine that I started with just 3x plus 4 to the 1/2. Well, when I differentiated this guy, I would have got 3x plus 4 to the -1/2. This is chain rule, times the derivative of whatever is inside, which in this case is 3, so it'll be 3. So I need to get rid of that 3 by dividing by 3 here. And the limits that I'm evaluating between are 0 to 4. So my limits, 0 and 4. 0 and 4. And that's equal to 32 over 3. Great. So now the area of Q. Well, that's the area of this guy minus the area of P. And the area of this guy, well, that went from 0 to 4, and then that was 4 as well. So it's more like a, 16 plus 1/2, 4 times the distance between, so this was 20 over 3, but that means that this little bit is 20 over 3 minus 4. I hope that's clear. So I'm just dividing it into a box and a triangle and measuring it, minus AP. And you will find that this is equal to 32 over 3 as well. So you see that the 6 marks, but there's only a few lines, and that's because it's really about this conceptual leap of realizing, getting really used to just integrating over functions to get the area underneath and understand that that's what they mean, and how to think about these geometrically. This and if you see these things that are just like a single power of x and no x squared or anything, inside a bracket that's raised to some fractional power like a half or whatever, you can do that. That is actually a really doable integral. And that is all for this lesson. Please let me know if you have any questions.